and have a good day everyone! Have you ever wondered how much distance a car needs to stop when a driver suddenly notices a danger on the road? In this presentation, we will use the principle of mechanics to analyze an emergency braking situation and understand how speed affects road safety. Mechanics is a branch of physics that studies the motion of objects and the force acting on them. In this case study, we focus on one-dimensional motion, which refers to motion along a straight line. To describe the movement of vehicle, we use concepts such as position, which is the location of an object relative to a reference point. And secondly is distance, which is the total length of travel from the initial position to the final position.
Hi guys, so before we start, let me introduce you to our members. First, Nur Balkis Shakina binti Ridwan, Muhammad Faiz Imran bin Hafizi, Nurish Sufia binti Zalanuddin, and Nur Alia binti Khairul Anwar. So let's get started and get into it.
Okay, now I will explain about purpose of the study. The purpose of this study is to determine the stopping distance by analyzing driver reaction time and braking performance at the specific speed. It also aims to evaluate pedestrian safety, with particular emphasis on visually impaired individuals who are more vulnerable in traffic environments. In addition, the study seeks to apply mechanics to real-life situations by connecting theoretical principles of motion, reaction time, and braking dynamics to actual traffic scenario. Next, I will show you guys about the problem statement. Imagine a busy street on a warm afternoon. Cars move steadily, and among them is one traveling at 50 kilometers per hour. Suddenly, a blind pedestrian steps onto the road, unaware of the approaching vehicle. The driver sees the pedestrian and instinctively reacts, but human reaction takes time, in this case, 0.8 seconds. Only after that pause do the brakes engage, and the car requires another 2.0 seconds to come to a complete stop. Can the car halt in time to spare the pedestrian? This moment of uncertainty captures the essence of pedestrian safety, especially for those who cannot rely on sight to navigate traffic. It highlights the fragile balance between driver awareness, reaction speed, and the mechanics of braking. A balance that can mean the difference between safety and tragedy.
Now we move to the calculation part. We want to find the stopping distance before the car hitting the pedestrian, so we must list down the given data first. Initial speed equal to 50 km per hour, final speed equal to 0 meter per second, reaction time equal to 0.8 seconds, and braking time equal to 2 seconds. Now let's begin the math. In mechanics, we might use SI units. Speed must be in meters per second, not kilometer per hour. To convert from kilometer per hour to meter per second, we divide by 3.6. Calculating that, we round it to U equal to 13.89 meter per second. So our car is moving at 13.89 meters per second. Now here is where our experiments comes in. We measured that it took 2 seconds for the car to go from 50 km per hour to a complete stop. So we use the formula for acceleration. A equal to V minus U over T. Substituting our numbers, A equal to 0 minus 30.89 over 2, we get A equal to negative 6.945 meter per second squared. So our car's actual braking deceleration is negative 6.845 meters per second squared. Now let's calculate the reaction distance. The formula for distance is speed multiplied times. So substituting our values, distance equal to 30.89 89 times 0.8 seconds. So we get distance equal to 11.11 meters. So this is our reaction distance. Now let's calculate the braking distance. Since we know the initial speed, final speed and deceleration, we use the kinematic equation that ignore times. The formula is v squared equal to u squared plus 2as. So as the given, v equal to 0, u equal to 30.89, a equal to negative 6.945, as is our braking distance which we want to find. Let's substitute the numbers and we get 0 equal to 30.89 squared plus 2 times negative 6.945 times s. So we calculate and we get the answer is 30.89 meters. That means after the brakes are applied, the car needs another 30.89 meters. Finally, we add both distance together to find the total stopping distance. So the distance total equal to reaction distance plus braking distance, and we substitute our answers we just calculated. Total distance equal to 11.11 plus 30.89. Adding them together, we get 25 meters. So our final answer is at 50 km per hour. This car needs exactly 25 meters to stop completely. Now, let's see what happens if we double the speed to 100 km per hour. We just used the same calculation as we just did before, and we found out that the reaction distance at 100 km per hour is 22.22 meters. And the braking distance at 100 km per hour using the same deceleration, negative 6.945, we get 55.56 meters. So the total stopping distance at 100 km per hour is 77.78 meters. Those are our exact calculation based on our real experiment. Now let's hand it over to next person to summarize our findings and give our final conclusion.
For the conclusion, the case study calculated the total stopping distance of a car travelling at 50 km per hour with a reaction time of 0.8 seconds and a braking time of 2 seconds. The total stopping distance is 25 meters, made up of 11.11 meter during reaction time and 13.89 meter during braking. The study shows that the car cannot stop in time if a pedestrian within 25 meter when the hazard is detected. It also highlights that stopping distance increases rapidly with speed when speed doubles from 50 km per hour to 100 km per hour. The braking distance increases from 13.89 meter to 55.56 meter. The total stopping distance rises to 77.78 meters. Overall, this emphasizes the importance of safe speed and sufficient stopping distance for road safety. Thank you.